the chemical properties of an atom, how it behaves, how it makes compound, which elements it makes compounds with, are determined by the number of electrons it has and how they are arranged. Atoms interact via their electrons. Their nuclei never come into contact. So every time we talk about chemical reactivity, we are talking about electrons. Electrons from one atom interacting with electrons from another atom. And we will see that not even all the electrons interact. Only the electrons that are further away from the nucleus. But more about that in a future slide. Again, the number of protons, what we call the atomic number, characterizes an atom, and we call an atom that has a particular number of protons element X. So as we saw in a previous slide, an atom that has 11 protons, atomic number 11, we give that the name sodium. An element is a pure substance, so all the atoms present have the same atomic number, and there are 118 elements with atomic number from 1 to 118, and the highest atomic number natural element is 92, is uranium. After that, all the other elements have been man-made. So the fact that elements, when they're on their own, require electron neutrality, requires that the number of electrons is the same as the number of protons. So an element that is not interacting with anything, that is on its own, has the same number of protons than electrons. But what about neutrons? Because neutrons do not have charge. They have mass, but not charge. So do the number of neutrons vary? And the answer is yes. The number of neutrons in a particular element can vary, and sometimes very widely. For example, I've got here the example of hydrogen. When you have a natural sample of hydrogen, imagine you have a little jar with loads of hydrogen atoms, you would actually have 3 types of hydrogens. You would have hydrogen, they all have 1 proton, because that's what defines that they are an atom of hydrogen, that makes them distinct as hydrogen. So they all have 1 proton, but they have different number of neutrons. Most of the hydrogen you would have in your little jar would be hydrogen with 1 proton and no neutrons. You have a tiny amount of a hydrogen with 1 proton and 1 neutron, so mass number 2, and then minuscule, and actually is radioactive, amount of hydrogen that has 1 proton and 2 neutrons. We call that the fact that you have, for an element, you can have a different mass number, a different number of neutrons, isotopes. So we talk about the isotopes of a particular element, and are all the different neutrons, all the different mass numbers that particular element can present. And they can be stable or they can be radioactive. And for example, in the case of hydrogen, the first 2 are stable and the third one is radioactive. And you might have heard about tritium. They don't get names except for hydrogen. The hydrogen one is called hydrogen. Hydrogen with 1 proton and 1 neutron is called deuterium. And hydrogen with 1 proton and 2 neutrons is called tritium. And you might have heard about the H bomb. So it can be quite famous. Isotopes are hugely important in a life and environmental context, from carbon dating, which is using a small and radioactive, small quantity, and radioactive isotope of carbon, carbon-14, MRI scans, medical resonance imaging in medicine, using medicine to image soft tissues, in which you use the hydrogen with 1 proton, mass number 1, so no neutrons, or radioimmunotherapy, in which you use a particular isotopes of particular elements to try to fight cancer cells. The applications of isotopes and the importance of isotopes is huge. So isotopes of an element will have the same number of protons and electrons, because that's what that element is, and different number of neutrons. And it varies. Most elements in nature will have somewhere between 2 and 10 isotopes. Typically, one tends to be more abundant and the others are much smaller, but that's not always the case. For example, in the case of bromine, the two naturally occurring isotopes of bromine, 79 and 81, have roughly the same proportion in nature. And hundreds have been created using nuclear reactions. So when we explore we test the boundaries of how elements can behave and how many neutrons we can get in a particular element. So for example, you've got here chlorine has two naturally occurring isotopes. One is chlorine 35 and one chlorine 37, and chlorine 35 is around 75%. In a natural sample of chlorine atoms, you will have 75% of them with the chlorine 35 and around 25% of chlorine 37. Oxygen has three isotopes. Oxygen 16 is the main one. I think 99.8% of naturally occurring oxygen, if you have a sample of oxygen, 99.8% will be oxygen 16. Oxygen 17 is a tiny 0.0017%. It's radioactive, so unstable. And oxygen 18 is stable, but with a very small abundance. I think it's 0.2%. So now I'm going to ask you to stop the video and just fill in this table for two of the most common isotopes of carbon, carbon 12 and carbon 14. There's another one, carbon 13, that is usually useful in chemistry. Stop the video now, please. So hopefully you stop the video and try the exercise, and hopefully by this point you're already experts in filling in this type of tables with this information. So if I tackle carbon 12 first, the atomic number is 6 and the mass number 12. And that means that I have 6 protons, as I would have 6 electrons, although the table doesn't ask me that. And because of the mass number is 12, and the mass number is the number of protons and the number of neutrons. If I have 6 protons, that means that I have 6 neutrons. And for carbon 14, again, the atomic number is 6, because that's what defines the element carbon that has 6 protons in the nucleus. So I put my 6 here. It has 6 electrons, so although the question doesn't ask you for electrons, and the mass number is 14. And the number of neutrons, therefore, is 8. In general, isotopes of an element will have the same chemical properties because they have the same number of electrons and the same configuration of electrons, and that's what determines how an atom is going to react. But they will have, for example, different physical properties because they have a different mass, they weigh differently, so properties like the melting point or the boiling point will differ because depend on the mass. There are 286 naturally occurring isotopes, and there are thousands of isotopes that have been synthesized via nuclear reactions. Despite the fact that they are unstable, they are radioactive, so they decay, they slowly lose their presence. They are used in research and they're extremely useful.